Welcome students. In this class we will learn how to integrate integral 0 to pi over 2 1 over a times sin squared x positive b times cos squared x times dx. This is a very important problem, and problems like this would be asked in several university exams as well as in competitive exams. So having mentioned that, it becomes imperative that we know how to do this question. So foremost, what I wish to do, I would like to start off with I being equal to, and then the next step would be I would like to take cos squared x out. Now if I were to take cos squared x out, this is going to be sin squared x over cos squared x. Of course the constant a has to be there, positive b because cos squared x is already taken out, times dx. The limits are 0 to pi over 2. Next, what I wish to do is I would like to rewrite sin x over cos x to be as tan x, and since we got sin squared x over cos squared x, I would be writing it as tan squared x, and 1 over cos x as secant x. Since we got 1 over cos squared x, this is going to be secant squared x. So this can be rewritten as integral 0 to pi over 2 secant squared x times dx divided by a times tan squared x positive b. Now I would like to make a substitution. Let say some p be equal to tan x, and if I were to differentiate this, dp is equal to secant squared x dx. So in place of secant squared x dx, I will be substituting dp. In place of tan squared x, it's going to be p positive b. Now limits, you got x is equal to 0, so p will be equal to tan 0, and x is equal to pi over 2, so p will be equal to tan pi over 2, which is equal to infinity. So this is 0 to infinity. Now it's tan squared x, so this has to be p squared there. Now what I wish to do, I would like to extract a out. Now if I were to do that, this is dp over a is taken out, so I would get p squared positive b over a integral 0 to infinity. So fair enough. Now what I want to do is I want to make the following substitution. Now before I could make the following substitution, I would like to rewrite this as dp over p squared. 1 over a can be taken out. Now b over a, can we write it as root of b divided by root of a raised to the power of 2? Now you might be wondering, why am I doing it? Because I want to resonate integral dx over x squared positive 1 squared. In other words, this 1 can be anything, so it can also be integral dx over x squared positive a squared, right? If I were to take a is equal to 1, then if a is equal to 1, this is going to be integral dx over x squared positive 1 squared. Of course we can apply the all important tan inverse formula. So having got that, what I wish to do is I would have to now make some substitution to represent this formula. Now directly I can apply this formula, but since we are starting off with this question, I would like to take, say, p is equal to some u times root of b over root of a, so that this is going to be dp is equal to root of b over root of a times du, and this would give us, if we were to substitute this over here, this is equal to 1 over a integral dp over, in place of p it's going to be u root of b over root of a, this is squared, and this would be a squared there, positive root of b over root of a squared. Now since we are talking in terms of u, what I would do is I will have to convert this dp to u. So I will write here as du, and then this has to be product multiplied with root of b divided by root of a. So I will place this root of b divided by root of a over here. Now this is equal to root of b divided, of course you might be wondering, I am not taking the limits into account. I will just fill in the limits within a minute. Root of b divided by root of a times a. Now this is going to be du I can take root of b over root of a squared out. If I were to do that, this is going to be u squared positive 1. Clearly you see that this is the formula that we have been looking for. Now this formula, integral dx over x squared plus 1, is nothing but tan inverse of x positive arbitrary constant c. So I want this to resonate this, right, this quantity, integral dx over x squared positive 1. That's the reason I made the substitution. Of course, we can directly from here we can apply the formula, but as I mentioned to you, since we are starting off, I don't want to place more complexity in the solution. So that's the reason I introduced one more substitution. So this can be rewritten as, I can flip this. If I were to flip this, I would get a, this is root of b over root of a raised to the power of 2. So this is going to be a over b. There is already a root of b over root of a, and there is another a here. So let me place that a over here. Now clearly what happens, this a and this a can be cancelled. You can just write this as 1 over a, and you got integral du over x square u squared positive 1. So this is the quantity that we have got. Now let me go back to the limits. Now this is a function of p. So we were looking for when p is equal to 0. So when p is equal to 0, if you were to substitute 0 is equal to u times root of b divided by root of a, you cross multiply, eventually you will get u is equal to 0. Fair enough. Now the next step is when p is equal to infinity. So infinity is equal to u times the root of b divided by root of a, and upon simplifying you get u to be as infinity. So the limits are not going to be changing. So 0 to infinity, 0 to infinity, and in this case 0 to infinity. So apply the formula. This is going to be root of b divided by b times root of a. This is going to be tan inverse of u. The limits are 0 to infinity. Now this can be rewritten as root of b divided by b times root of a, and tan inverse of infinity negative tan inverse of 0. Tan inverse of 0 goes off. Tan inverse of infinity is pi over 2. So you can place pi over 2 times the root of b divided by b times root a. Like this, you can write this as pi times the root of b divided by 2 times b, and then write it as root of b times root of b followed by root of a. So a b and a root b can be cancelled, giving me pi over 2 times root of b times root of a. This can be rewritten as pi over 2 times root of ab units. So either you can stop here or you can come all the way here and write this in. If they ask you this in multiple choice question, and if they give you this, then obviously you will have to reduce the solution right all the way to this particular point. So having given you this, please like, share and subscribe to our channel so that you might train yourself in all problems connected with integral calculus. Thank you, students.